Okay, everybody, so here's our notes on section 1.3. This is one I've been meaning to type up forever here and have never quite gotten around to that, but I think we'll muddle through and we'll be okay. So 1.3 is on basic classes of functions here, just trying to give us a little bit of a refresher on some of the things that we've learned over the last couple years about types of functions that we're likely to see a lot of. And the first and most basic of those classes of functions are polynomials. These are really the ones that you cut your teeth on when you started understanding what a function actually was. And without using the phrase polynomial functions, you've been using this ever since you got to the beginnings of algebra back in probably 6th or 7th grade math. So our semi-formal definition of a polynomial function is one that can be written this way: a times x to the n power plus b times x to the n minus 1. And you start to see a pattern now. Each successive term has the same base, that being x, which is the only variable within this function. Let's keep that in mind. They can have different coefficients, a, b, and c, although those numbers certainly could be the same, but they do not have to be. And the important thing here is that each one of those variables, x, has an exponent now that has to be an integer. I don't believe it says that anywhere up here, but you'll notice that in each term, the degree there, the value of that exponent is going to go down by 1 until eventually we get down to our constant term. And for really bad reasons right here, we tend to use k as the variable here for constant. I think because it makes the same sound as a hard C, which constant begins with, but we had already used c for our third coefficient. So that's what a polynomial function tends to look like. And it does say here, I'm sorry, where n can be any positive integer. But that's important to note, everybody. N cannot be a negative number. We know how to deal with negative exponents, like x to the negative second power, but that is outside the definition of a polynomial. So to be a polynomial, all your exponents need to be positive integers. And the only other little thing to add on there, technically, as these exponents go down, maybe this was a 3 and a 2 and a 1, eventually you get to that last term that technically has an x to the 0 power right over there multiplied by k. But of course, any number to the 0 power is 1, and so we don't have to bother writing that out, and we just leave that term there as k. So examples of polynomial functions, as I said, a lot of things you've been dealing with since pre-algebra. So right here, f of x is equal to 3x minus 7 is really about the simplest type of polynomial function we can get, that of course being a linear function. Linear functions are any polynomial with a degree of 1. Moving on just a little bit beyond that, we have quadratic functions, polynomials with a degree of 2. So g of x is equal to 5x squared minus 3x plus 2. And then, of course, we've got more complicated ones. And this one right here, h of x, is an example of what we call a quintic function. Quint, there's that prefix right there meaning 5, this is a 5th degree polynomial here as well. And we could sit here all day long and try to come up with examples of different types of polynomials, but I think you get the point here after just a few of them there. All right, the most interesting thing about polynomial functions is the fact that they all follow certain rules here for end behavior. We know what polynomial functions do at their far extremes, either as we go way to the left as x approaches negative infinity, or as we go way to the right as we are approaching positive infinity. And actually, now that I say that out loud, I realize I don't like the way that I did this right here. I'm going to change these around, guys. The negative infinity is on the left, so I'm going to put that first, and the positive infinity is going to be on the right, so I'll put that one second. Now, the big takeaway from this, if you didn't know this already, is that unlike a lot of other types of functions that are out there, every polynomial function either approaches infinity or negative infinity at its ends. And you'll see what I mean by that when we talk about a couple of graphs in just a second. So let's deal with a simple one here. F of x is equal to x squared. And the questions I'm asking in these two boxes over here are, as x approaches negative infinity, what happens to your value of y? Now, I'm hoping that eventually, if not already, you guys can kind of close your eyes and imagine this and think about what's happening. But for now, it certainly isn't the worst idea to go ahead and draw ourselves a picture of what y equals x squared looks like, and that being an upwards opening parabola that looks like this. And as we try to answer the first question here, what happens to f of x as x approaches negative infinity, think about this as a track on a roller coaster, everybody, and you are in your car right over here, and as x approaches negative infinity, we are moving this way. We are moving from right to left. Well, as I think you can see, your y value here is increasing without bound. So our end behavior right here would be that f of x is approaching positive infinity as x approaches negative infinity. So one more time, as we move from right to left, y is increasing without bound. And then to reverse that now, as x approaches positive infinity, we're now moving from left to right. And we can see now that after bottoming out there, this function is again going to increase without bounds. So f of x is going to approach positive infinity here as well. So with this particular polynomial function, regardless of whether x is approaching negative infinity or positive infinity, our end behaviors here are the same. This thing shoots up on both the left and the right-hand side. But that's certainly not the case for every polynomial that's out there. Let's take a look at this one, a cubic polynomial with a negative leading coefficient. So again, it'd be great if we could learn to do this without, but for now, if we need to draw a quick graph, let's go ahead and do that. And this graph right here, I hope we remember what x cubed normally looks like. Putting a negative in front of it flips this thing so that it's going to look something like that. So the question first becomes, what happens to the value of y, or f of x, as x approaches negative infinity? So if I transfer our little roller coaster car down here now, as we move this thing from right to left, as we go further and further left, we see that our y position is going further and further up. So just like the last one right here, f of x is approaching positive infinity as x moves from right to left. But as we reverse course now, as x approaches positive infinity, moving the wrong one there, no, that, well, it's there somewhere. Anyway, all right, so now as we're moving from left to right, now our y value is dropping and will continue to do so forever. So now for the first time, we're going to say that as x approaches positive infinity, our f of x value is approaching negative infinity. This thing goes down to the right and will continue to do so forever. Let's look at a third example here. Actually, and I lumped these two together here kind of to prove a point. These don't look like the same function. We have a negative quartic function, which is fourth degree, and we have a negative quadratic function. But the important thing about these two is that they have two important characteristics in common. Number one, they both have a negative leading coefficient. And number two, these are both even degreed functions. The first one is a fourth degree function. The second is a second degree function. And if two polynomials have those two things in common, then their end behaviors are going to be the same. If you needed to draw these out, the first one, the negative fourth degree function, very likely looks something like this. The second one, which is a negative second degree function, is a downward opening parabola that looks like that. But what I'm hoping we have figured out already, or maybe we just remember from last year, is the following. And the first two examples here kind of illustrate the point I'm about to make. When a function, a polynomial function, has an even degree, your end behaviors are going to be the same. Either it goes up on both sides or it goes down on both sides. But when your degree is odd, like this cubic function right here, your function has different end behaviors. It goes up on one side and down on the other. So back to this example right here, this one we're just working on, although it's really two different functions, both of these are even degreed functions. Their highest power is even. That means they have the same end behavior. And because they have negative leading coefficients, both of them, that means that they go down on both sides. So the graphs kind of illustrate what I'm about to write, although I'm really hoping, like I said, that you guys would be able to figure this out without it pretty soon. On both sides, everybody, as x approaches either positive or negative infinity, y is going to approach negative infinity on both sides because of that negative leading coefficient that we have in both spots. Okay, the last one I thought I would put up here just for fun. It's important to realize that this function that I've drawn in red, unlike the other ones that were blue, the reason it's in red, it's not a polynomial, everybody. But I just wanted to put this up here to illustrate to you that not all functions do what polynomials do. The first thing I want you to realize is that 1 over x can be rewritten a different way as x to the negative first power. And that right there violates a rule that we just wrote down on the last slide. Polynomials cannot have negative exponents. That's why this one doesn't follow the rules that we just discussed in the previous three. And I'm hoping that you guys remember your parent graph here for 1 over x, which is a hyperbola that exists entirely within the first and the third quadrants and uses the x and the y axes as its asymptotes. So just kind of to get the sense of what's going on right here, the first column is going to ask us what happens to our y value as x approaches negative infinity. So back to the little roller coaster car. Can I steal this one down? There we go. And as we are approaching negative infinity, moving from right to left, I've actually got to jump down here now. And as we move from right to left, our y value continues now to increase, but ever so slightly, and it looks like it's approaching not plus or minus infinity, but it looks like it's approaching the x-axis, which is a y value of 0. So here we would say that as x approaches negative infinity, f of x value is approaching 0. Now, I kind of have a made-up notation for this that people haven't really seen before, and you'll never see again, so don't think it's important, but it kind of makes some sense. I would actually love to put a little minus sign after that. And what I mean by that, no, that does not mean negative 0. But what I mean by that is that y is approaching 0 from the negative side. This graph right here, guys, yeah, your y value is getting closer to 0, but all these y values are negative. So we're approaching 0 from the bottom, moving up towards it very, very slowly. I did that again. All right, so that's that. And now as we look at the second part over here, as x is approaching positive infinity, let's talk about what's happening to y now. So now I'm going to jump over the y-axis, and as we move from left to right, our x value is increasing towards infinity, and our y value is once again approaching 0. Except now it's doing so from the top side, from the positive direction. So if I were in charge of the world, I'd put a little plus after that 0 there to indicate that it's approaching 0 from the top. So again, everybody, just to clarify, this last example that we just did there in red does not belong in this table right here for end behavior of polynomial functions. The first three are polynomials. This one down here is not, but I just wanted you guys to see that not every function approaches positive or negative infinity as x goes out to the extremes. But every polynomial function does approach either positive or negative infinity. And again, hopefully you'll be able to do that soon without drawing the graphs out. Okay, shifting gears now, guys, we're going to move on to our second class of function, rational functions. And these ones you started to see just a little bit of in Algebra 1, but it really wasn't until Algebra 2 that you guys dove into rational functions and really started to understand what they are. The word rational is an important word in math, although a lot of us have probably ignored learning what it means up until this point. And rational is really just a mathematician's way of saying fraction. So a rational function, in a simplistic way of looking at it, is just a function, such as f of x right here, that can be written as the quotient of two other polynomial functions. So f of x needs to be written as the quotient of g of x divided by h of x, but both g of x and h of x need to be polynomials in and of themselves. So when we divide a polynomial by another polynomial, we end up with a rational function. So here's the function we just got done talking about. F of x is equal to 1 over x. This is probably the simplest example we can come up with of a rational function. It is the quotient of two polynomials. Let me start with the bottom actually. y equals x is about as simple of a polynomial function as you can come up with. Technically speaking, everybody, the numerator here, the 1, is a polynomial also. It's just a pure constant that doesn't have any variables in it whatsoever, but you really could think of the denominator as a simple first-degree polynomial. You could kind of think of the constant up on the top as a simple 0-degree polynomial. So yeah, 1 over x is a rational function. It gets more complicated than that, of course. Here we have the quotient of two linear functions. F of x is equal to x plus 3 over x minus 4, and this is one that you've actually done a lot with over the last couple of years in terms of graphing, and we should be able to come up with a very accurate graph of a purely linear rational function there. Linear on top and linear on bottom, and there we go. Okay, little bit of talk here about asymptotes, everybody, speaking about rational functions, and we talked about this a second ago. So here's what we've got here, guys. If we want to compare asymptotes, I'm sorry, I really should have kind of done a header right there. So let's discuss the concept of asymptotes. Fun word to say and to spell. Here we go. If the degree of g of x, which if you go back to our definition right here, g of x was our numerator. If the degree of your numerator, your top, is less than the degree of h of x, which is the bottom. So if the degree of the top is smaller than the degree of the bottom, we are always going to have a horizontal asymptote at the line y equals 0. Otherwise known, I hope we remember here, the line y equals 0, otherwise known as our x-axis. Okay, second possibility here. Oh, I'm sorry, I wanted to do just a quick little talk about this. So y equals 1 over x is an example of what we're talking about. The degree of our numerator is 0 because it's a constant. The degree of our denominator is 1, that's a linear function, so that meets this criteria. So, as we said, we have a horizontal asymptote right here at the x-axis. We'll talk more about vertical asymptotes in just a minute, but for now, that is just the y-axis, and that is why this graph tends to look a little something like this, having that horizontal asymptote right there at the x-axis. We're going to talk more about horizontal asymptotes in Chapter 2. We're actually going to redefine them and talk about that being a little bit different than you guys might have learned that definition over the last couple of years. But for now, let me just say that your pre-calculus definition of asymptote, being a line that your function approaches but never actually touches or crosses, it's going to work for us in this chapter. In Chapter 2, we'll talk about how a function can actually cross its asymptote, not just once or twice, but actually an infinite number of times, but that's a definition that involves limits, which we haven't gotten to just yet. Okay, so that is case number 1 for horizontal asymptotes. Our second case, if the degree of your numerator, g of x, is equal to the degree of your denominator, if you have the same degree on both the top and the bottom, then we have a horizontal asymptote at the line y equals a over b. And going way back to our definitions, actually I don't know that I put that here or not, what a and b are is they represent the leading coefficients of both the numerator and denominator. All right, leading coefficients. This is probably better illustrated with an example rather than trying to write out a definition here, okay? So if we had a function that looked like this, y is equal to 3x squared plus 1 over 6x squared plus 7. First question, is it a polynomial? Answer to that is yes. Is it a rational function? Yes, because we have polynomials on both the top and the bottom. The degree of the numerator is 2. The degree of the denominator is 2 also. It's a tie. So when that happens, we have a horizontal asymptote at the line, let me write this out, horizontal asymptote at the line, y equals, and now we do this quotient of a over b, everybody, the quotient of your leading coefficients. So the leading coefficient in the numerator is 3, and the leading coefficient in the denominator is 6. And of course, we would simplify that to get y equals 1/2 for our horizontal asymptote. Now, one thing I think you all know, but I want to go ahead and just say, don't be fooled by the order of the terms in a polynomial. You guys know that that's irrelevant. If I was to rewrite the numerator in the opposite order as 7 plus 6x squared, that really didn't change anything at all, but I think you guys know this. The leading coefficient of the denominator is not 7 now. It's still 6. Leading doesn't mean which term comes first. Leading really means the coefficient of the highest degree term within that polynomial. So if I were to leave the problem like this, that wouldn't change anything, and our horizontal asymptote would still be the line y equals 1/2. All right, let's get that back to where it was. And then, of course, the third case, everybody, if the degree of your numerator, g of x, is greater than the degree of your denominator, which is h of x, this is the case we like, everybody. There is no horizontal asymptote. Now, I don't want to go into too great of detail right now, but some of you have learned over the last couple of years that in this particular case, there is often something called a slant asymptote. Okay, that's what happens specifically when the degree of g of x is exactly 1 higher than the degree of h of x. That's when you end up with a graph that usually has a vertical asymptote like this, but also has a slant or a diagonal asymptote like this, and your graph ends up looking something like this, which can be a little wild, everybody, but we're not going to get into too great of detail as to how that works. In fact, if you really want to get crazy, if the degree of your numerator is 2 higher than the degree of your denominator, you actually get a parabolic asymptote. So instead of drawing a red line, we would have drawn a red parabola. And we can continue to take that idea up a ways. But as I said, that's probably more complicated than we need to get right now. Take a look at this example I gave you, which is a little bit weird. Okay, I don't know why I spaced this out the way that I did. But if we had y is equal to x squared over x, my first question for you guys would be, is this a rational function? Well, technically, the numerator's a polynomial, the denominator's a polynomial, so yes. And since the degree of your numerator is higher than the degree of your denominator, 2 is greater than 1, there is no horizontal asymptote. But some of you probably looked at this right away and said, well, wait a minute, that's stupid. Why would you write the function that way? X squared over x just simplifies to y equals x. And guess what? You're not wrong. Think about what the graph y over x looks like, and hopefully everybody remembers that it's going to look like this. The only difference now is that our original function right here of x squared over x cannot have a 0 for your value of x. You'd be dividing that out. So technically there's an open circle right here. That is what this graph really looks like. But the important question is, everybody, does this graph, with or without the hole in the middle, does this graph have a horizontal asymptote? And the answer to that is no, it doesn't, and that kind of supports this idea right here. Okay, so moving right along right here, graphing rational functions, and this is one that I talked with you guys about a second ago. Let's take a look at what we call a bread and butter rational function, the quotient of two linears, x plus 3 over x minus 4. And I'm hoping you guys remember how to do this by hand, and if not, not the end of the world here, guys. With rational functions, we have asymptotes, and I haven't talked at all about vertical asymptotes just yet, but this is an easy one that people tend to remember. Vertical asymptotes come from values of x that would make the denominator equal 0. So what we would do right here is we would set x minus 4 equal to 0 and solve, and we would end up with x equals 4. The only way that this would not be a vertical asymptote is if x equals 4 was also a 0 of the numerator, and if there was something we could factor and cancel. But plugging a 4 in right here is going to give us 7, not 0. So yeah, this one is in fact a vertical asymptote at x equals 4. So on my graph, I'm going to go 4 units to the right of the origin and draw my vertical asymptote right there at the line x equals 4. Next thing we're going to consider, what is our horizontal asymptote? And that involves a lot more thinking than the vertical asymptote. So this goes back to the three cases we just considered. So we've got to look at the degree of the numerator and the denominator. Well, both the numerator and the denominator are linear functions, so it's a tie. They've got the same degree. So for our horizontal asymptote, that comes in at y equals, and it's the quotient of a over b, those being your leading coefficients. Well, as luck would have it, your leading coefficients again here are both 1. So y equals 1 over 1, or 1, is the one and only horizontal asymptote we have in this function. Okay, and there is the line y equals 1, and that's that. So what's happened now, guys, is that we've drawn both a horizontal and a vertical asymptote. They intersect right over here at the point 4, 1, and those two asymptotes have divided the coordinate plane into 4 regions. Now, I was going to ask you guys, what do you call one section or one region out of a total of 4? And the answer to that is a quadrant. We've made 4 quadrants, not the normal 4 quadrants that are created by the x and the y axes, but 4 quadrants nonetheless. And what I'm hoping you guys have learned about rational functions is that they will exist in 2 out of those 4 quadrants. Now, which 2 out of the 4 is interesting? And I want to just consider a couple of possibilities. I think you guys know the answer to this already, but humor me for just a second. Ask yourself for a moment if it's possible for your rational function to exist in the top right quadrant and the bottom right quadrant, I drew that too low, at the same time. The answer is no. That is not possible, because right there, this is a rational function, and functions must pass the vertical line test. And if I draw something in both the top right and the bottom right, right there I see 2 points of intersection. This graph, this relation, fails the vertical line test, and it's not a function. Now, knowing that this, what we're graphing here, is a function, working backwards now, I know that the graph I've drawn cannot be correct. Likewise, this function cannot exist in both the top left quadrant and also the bottom left quadrant for the exact same reason. It fails the vertical line test yet again. Here's a question you may not have considered. Can a rational function exist in the top left and the top right quadrant? The answer to that is yes, it can. This graph that I've drawn right here does pass the vertical line test. This is a function, and it can happen. It doesn't happen as often, and it requires a little bit of a trick that I'll show you guys a little bit later. Likewise, the same graph really could exist in the bottom left and the bottom right. I shouldn't have drawn all that at the same time. But what I think you guys know is that the overwhelming majority of your rational functions tend to exist in kitty corner quadrants, either top right and bottom left, or let me switch to green now, top left and bottom right. It tends to be one of those two cases, either the blue or the green, the majority of the time. But it's not a guessing game, everybody. So what we're going to do here is consider just 2 quick and simple x values, one to the right of your vertical asymptote and one to the left of that asymptote. So let's just pick any old x value greater than 4, and probably the easiest one to deal with would be 5. And if we were to go simply and evaluate this function at an input value of 5, 5 plus 3 in the numerator gets us 8, 5 minus 4 in the denominator gets us 1, we know for a fact that this graph has to pass through the point 5, 8. So I'm going to go to 5 and my 8, it's right about there somewhere, not great spacing, but okay. That tells me what I need to know. That tells me that this rational function exists in the top right quadrant. Beyond that, it's a waste of your time and intelligence and experience at this point, everybody, to test more points that are over there to the right. You know what rational functions do, and you know what purpose their asymptotes serve. They're like force fields that kind of draw the function close to them, but don't allow it to actually touch. So, let me extend this vertical asymptote up a ways. This function is going to start high here and come down and look something like that. I wish I had a little more space, but it does something like that, and I'm not concerned about getting a great deal more specific than that. Now I know your inclination is to assume now that because this function exists in the top right quadrant, it must also exist down here in the bottom left. You are probably correct in that assumption, but we don't like to assume too much here at this level, so let's choose an x value to the left of the vertical asymptote. X equals 3 would make a lot of sense, but honestly guys, 0 is probably the easier number to pick. So plugging a 0 into f of x, we're going to get 3 on top and a negative 4 on bottom. So we get the ordered pair of 0 and then negative 3/4, which is going to get us to this spot right over here. And sure enough, the existence of that one point does verify that, yep, this thing exists in the lower left quadrant. And here I've got a little bit more room to draw this properly, and it's going to look something like that. You guys will notice that the way I started drawing this function right over here, at least for a time, I almost drew it parallel to that horizontal asymptote. It isn't. To be parallel to a horizontal line, I would have had to draw a horizontal line, and this function from left to right is purely decreasing and always decreasing, but at least way out there it's decreasing at such a slow rate that it almost looks horizontal right there. So everybody, that's our graph for this first one, what we would consider to be a simple rational function. Let's take a look at what else we have going on here, guys. A few more left to go. This one's a little bit more complicated, although in a way it's actually easier than the one that we just did, and let's discuss what's going on right here. We have ourselves a rational function with a polynomial on top and a polynomial on bottom. But what I'm hoping you guys recognized right away before I've started to say it is that x squared minus 25 is a special binomial. It's a difference of squares. And I'm hoping at this point your mathematical instincts kick in and you realize that, oh, that factors into x plus 5, x minus 5. And the denominator, of course, stays put at x minus 5. Guys, factoring is one of those skills that you learned probably 4 or 5 years ago, and any time it occurs to you that you could factor a polynomial, you should do it. Factoring is almost always worth the time and the effort. And now what you've probably realized is that we have an identical factor on both the top and the bottom of the x minus 5. Now notice, it is the entire factor, x minus 5, that cancels out all at once. What you cannot do, everybody, is cancel term by term with this and this. Because then by that rationale, you could cancel out that x, and now you're just lost in the ether floating around aimlessly right here without any structure. You're an amoeba, mathematically speaking, and you don't want that. So we cancel out entire factors, not terms. So the entire x minus 5 on both the bottom and the top cancel, leaving us with just the linear function of x plus 5. So let's talk about what we're supposed to do with this. Obviously, we're going to try to graph this function. We started off with this function right here, x squared minus 25 over x minus 5, and we whittled it down to x plus 5. I think we can all agree that this function is easier to graph than the original one, so we should graph that one. Y equals x plus 5. Let's do that. It's a linear function with a y-intercept of 5 and a slope of 1. So that would go here and down, and there you go. And the graph of y equals x plus 5, this is not a trick question, everybody, is just going to look something like this. But the important question is, the two functions that I've put in black boxes now, are they identical? And the answer to that is no. It's a question of domain. If I were to ask you guys, what is the domain of this function right here, x plus 5, what values can you put in for x, and then everybody forgets the rest of that sentence, what values can you put in for x and get a real number out for your result after you add 5 to it? The answer to that is that this function has a domain of all real numbers. But if I were to ask you the same question for the original function right over here, I think we can see right away that there's one value of x that we could put in that will not get us a real result. That is the value of x that would make the denominator equal 0, and that would be 5. So for the domain of the first function, x cannot equal 5. So these two functions, the blue one in the black box and the green function in the black box, are what we call functionally equivalent. They will give us the exact same result for every value of x that is in both functions' domains, but they don't have the same domain. This one in blue, which is the one we were really tasked with graphing, has a domain of all real numbers other than 5. So, if we've forgotten this from the past, when you see this right here, a common factor canceling out on both the top and the bottom, that, everybody, is what we oh so formally call a hole within your graph. Really, the formal term for that is a point discontinuity. We'll get into that more in Chapter 2. So what that means, well, what it really means is I haven't drawn my graph very well or set it up good. All right, if I move all of this down just a little bit here, guys, that means that we've drawn this thing correctly up to a point. But when this gets to the spot where x would be equal to 5 normally, there's a small hole right there that we indicate with an open dot. How small? Infinitesimal. That point right there has no size and no area, but you need to draw that pretty big to make clear to me that you understand that 5 is not in the domain of this function. And I think the y value going along with that, everybody, I can get that from this spot right over here. 5 plus 5 would be 10, so we've got a hole right over here at the point 5, 10. 5 is not in the domain of this function. 10 is not in the range of this function because of that hole. So going back to the previous problem, take a look at your denominator, x minus 4. When x was 4, that was a vertical asymptote. In this problem, we could have approached that the same way. Look at your denominator, ask what x can't be, and that answer would be 5. But in this problem, because 5 was also a 0 of the numerator, that becomes a hole, not a vertical asymptote. So really, in your hierarchy of what to look for, we should be factoring, canceling, and looking for holes first, then vertical asymptotes, and then horizontal asymptotes. Okay, and the last thing we're going to talk about is a big concept in this section, is how to combine different types of functions. People remember these pretty well, so I'm not going to spend a whole lot of time in theory here. We're just going to do some examples. There are 5 ways, everybody, of combining functions. And the first 2 right here, 1 and 2, I'm really putting together, involve either adding or subtracting 2 functions. And this is something I don't think you guys need a whole lot of help with. If you're going to take g of x and add it to f of x, that is simply written in this format right here, g plus f of x. And obviously the other way is with a minus in there as well. But of course subtraction and addition are really the same thing. So if we're going to use these 2 functions right here for our examples, g of x is going to be x squared minus 3x. F of x is going to equal 2x plus 1, and I were to ask you guys what is g plus f of x, I would kind of read this statement right here backwards, okay, from here to here. G plus f of x means that we're supposed to take g of x and add it to f of x. Okay, I can do that. My definition of g of x was explicitly given to me right there. G of x is x squared minus 3x. We're going to add to that the definition of f of x, which is 2x plus 1. And things you don't need to be told, everybody. Anytime you can simplify an expression, you should do that. So this is going to become x squared minus x plus 1. Ta-da! Circle it, and we are done. But unfortunately, this is one of those things that people can do without really understanding what it is that they've done. So I want to take just a moment and explain something to you guys real quick of what it is that we have accomplished. If we were in class right now, I would ask somebody to spit out a random number, and I'd call on Bob, and Bob would say 11. Okay, so we're going to go with that. So I'm going to ask you guys a couple of questions. With these functions right here, what is the value of g of 11? Oh, I had to pick a hard one. 11 squared is 121. 3 times 11 is 33. And 121 minus a 33, I believe, is going to get us an 88. Boy, I sure hope that's right. 121 minus 33. 11 minus 3 is 8. 11 minus, yeah, okay, that should work. Good. All right. Then I would ask you guys, what's f of 11? And 2 times 11 is 22, plus a 1 is 23. Okay, so if I were going to ask you guys, looking right here, what is the value of g of 11 plus f of 11? Well, right now this isn't real hard because we've already done the work. G of 11 we found was 88, f of 11 was 23, and if we were going to put those two together right there, we're going to get 111, that's kind of cool, I didn't realize that, for our answer. But the other thing to consider is what is the purpose of this? The answer to our question, g plus f of x, was x squared minus x plus 1. So what I want you guys to realize now, and I tell you what, I wish I'd given myself a little more space right here, but okay, we'll cram this in here. If I were now to ask you guys, let's use this definition right here, what is g plus f of 11? Well, using this definition right here, guys, we're finding here, we should find, that that's equal to 11 squared minus 11 plus 1. And let's see what happens there. 11 squared is 121, minus 11 is going to get us 110, plus 1 is going to get us the same 111 that we got right here. Now, that really shouldn't shock us. I don't know that it does, but this was, again, just totally random. So the way we got this answer right here was really a three-step process. We evaluated g of 11 first, then f of 11 second, then we added those two numbers together third and got 111. But once we figured out what the sum function was, then it really becomes a one-step operation, albeit a more complicated one-step operation, but there you go. And in one step, we were able to get the same result. I don't know if that amuses anybody, but that's kind of what we just did. All right, let me draw a big black line going across, and let's move on to what are really the third and fourth ways of combining two functions here, and that's multiplying and dividing right here. Actually, I take that back. This is really just the third way. Division I wrote separate underneath. So f of x multiplied by g of x gets rewritten really in that format, everybody, fg of x. So, in red, if I was going to ask you guys to find fg of x in reference to these same two functions up above, let's write that out. Okay, just reversing the definition on the top, fg of x means that we are going to do f of x multiplied by g of x. Well, we already knew that the explicit definition of f of x was 2x plus 1. The explicit definition of g of x was x squared minus 3x. And now again, you don't need to be told this, we're going to have to FOIL that out to simplify. The 2x times the x squared is going to get us a 2x cubed. The outer product is going to be a minus 6x squared. The inner product is a plus 1x squared. So that's going to be a minus 5x squared. And the last product is going to be a minus 3x. So, I guess putting all this together here, guys, that is our answer to this question, that fg of x is equal to 2x cubed minus 5x squared minus 3x. That is a little bit complicated to do with the 11 that we talked about before, so I'm going to ask you guys to trust me on that one. And the fourth way now of putting them together is just the quotient right here, that f of x divided by g of x can simply be written as f over g of x. The one thing, of course, you have to watch out for here is provided that your denominator, g of x, cannot equal 0. That's the one time that all the rules for division just get thrown out the window. So again, our definition for this one right here, f over g of x, could just be rewritten as f of x over g of x. Okay, f of x, we said, I have it right here above me, was the 2x plus 1. The gx right underneath that is the x squared minus 3x. And guys, division, of course, is the most complicated of those four basic operations that we've talked about. But in this case, most of the time, you're going to write it this way and then be done. All I would tell you in general terms is to simplify this expression if you could at all but 2x plus 1 doesn't factor. The x squared minus 3x, all you could do is factor x, but that would cancel with anything on the top. This one, everybody, is as clean as it's going to get, and that's that one. So that's division. The fifth way of combining functions is unique to functions themselves. Adding, subtracting, multiplying, and dividing, that works with numbers and all sorts of things. But the fifth one, composition, only applies then to functions. It's not really possible to compose two numbers right here. And the definition of composition, well, this is really just a different way of writing it. We would read this right here as f of g of x. And you would also see it written this way, which a lot of people call fog, but really we would say f comp g of x. All right? And what it is it's taking x and using whatever number this is as the input value into the g function. But then you do what g of x tells you to do and take the output value from g and use that as the input value into f. All right, so let's see that as an example right here. You know what, before I dive into this, let's do the same two functions we were talking about, and let's try to make life maybe just a little bit easier here. So where I was in the last problem, let me just copy and paste those, everybody. This is a little bit of a mess here, but let's take this. All right, and let's copy that. Let's bring that over here, and let's paste that over here on the side there somewhere. Kind of a lot going on. And let's do something that's maybe a little bit simpler. No, let's keep it in general terms right here. So if we were going to do f composition g of x, the first thing I would tell you guys to do, like always, is with parentheses, work inside out. We've got g of x on the inside and f by itself on the outside. So I would rewrite the f alone, and inside this set of parentheses, where there used to be a g of x, I would replace it with what g of x is, which is x squared minus 3x. Now, as weird as it is, everybody, that, which cannot be simplified, now becomes the input value into the f function. And the f function is 2x plus 1. Or another way to think about this when I'm explaining it to Algebra 1 and Algebra 2 students is to stop saying x and start saying the word something. F of something is 2 times that something plus 1. So our input value now isn't a number, it's a function. And f of something is 2 times that something plus 1. Let me make sure I had that right. Yeah, and the input value now is simply x squared minus 3x. So it is 2 times that something plus 1. We understand it better when that input value is like a 7 or an 11, but for now, it's an expression. And of course, we would simplify this by distributing and come up with a 2x squared, a minus 6x, and then a plus 1. And that would be the value here, everybody, of f of g of x. And I tell you what, I do want to run with this. I want to go with an easier input value right now than 11, because that would make things a little bit more complicated. Why don't we deal with maybe a 5 right now? And let's go ahead and evaluate f of 5, which is going to be 2 times 5 plus 1. That's going to be an 11. A g, actually, I'm not sure that we needed that. A g of 5 here, I'll show you why in just a second. Oh, that's really funny. A g of 5 is going to be 5 squared minus 3 times 5. That's 25 minus 15. That's going to be 10. Let's keep that in mind. So if I were now going to ask you guys, what is f of g of 5? I think I know the answer by plugging that directly in here, but let's do it a different way. This is really f of, and inside that parentheses is g of 5. Well, we just evaluated g of 5 and found that it was equal to 10. So 10 is the output value of g when the input value was 5. But that 10, which was now the output of g, now becomes the input value into f. And once more, everybody, f is telling us to take 2 times your input plus 1. So this is 2 times something plus 1. And this time, that something is 10. And 2 times 10 is 20, plus a 1 is 21. Now, what does that prove? Absolutely nothing right now, until I go back to this level right here and realize that we came up with a new function, 2x squared minus 6x plus 1, that gives us, or should give us, the value of f of g of x. So right here, let me shift in green here, guys, and ask us now, what is f of g of our original input value of 5? It's the same question that I asked you right here, but now we're going to use this new function that we came up with. So this is going to be a 2 times 5 squared, that is going to be 50, minus 6 times 5, which is going to be 30, and then plus 1 at the end of all that. 50 minus 30 is 20, plus 1 is going to get us the same 21 that we came up with right here. So there's really two different ways of getting that same result. This way right here was kind of the brute force method. We went ahead and evaluated g of 5, which was 10, and then put the 10 into f. This way here took more work up front to come up with this new function right here, but at the end then, that became relatively simple to evaluate. And the last thing I was going to talk about with this example here, and we might have noticed, is what happens when you compose a couple of special functions. So watch what happens when I do this real quick, guys. F of g of x. All right, so that is going to be f of, and g of x is x minus 1 over 3. Well, f is telling us to take 3 times your input plus 1. So 3 times something plus 1. And that input is x minus 1 over 3. Well, check this out. That 3 divides out with that 3 right there, and we're left with x minus 1 plus 1, which just gets us x. The same thing happens with g of f of x. So that's going to be g of, and f of x is 3x plus 1. G of x is telling us to take something minus 1 and divide the whole thing by 3. Well, that something now is 3x plus 1. So what happens here in the numerator? The plus 1 minus 1 cancel, and the 3x divided by 3 just gets us x. Now, normally, you guys, composition is not commutative. You don't get the same result by doing them in different orders. But in this case, we ended up with the same answer both times. And not just any answer, we ended up with x, which is significant because that was the input value with which we began. You started off putting x into g, and when you took that result and plugged it back into f, you ended up with the same number that you started with. When this happens, everybody, when f of g of x is equal to g of f of x, this is where we get two functions that are inverses of one another. You get inverses if f composition g of x is equal to x. If that happens, then g of f of x will also be equal to x as well. All right, guys, we're going to wrap it up right there. That is everything we wanted to cover right here in section 1.3. So let's give that homework a shot and see how we do.